Today we'll be discussing about welded connections. Okay, now in connections we have two types of connections that we have for this course. The first one was bolted connections, and now we have a good picture about bolted connection. Now welded connection is yet another type of connection which is also widely used. You see that everywhere, almost any type of structures which involve welding. In type of structure which involves steel has welding in it. So it is a this is a technique which is in good practice. So we'll be just going through an overview is to see what are the things that you need to know for this course regarding weld, and then we'll be going through something called weld subjected to direct force. Now I'm pretty sure that you have a good idea about direct. When I say direct, it means that the load acts along or the load passes through the centroid of the connection. We were talking about bolts, and we know that a direct forces acting on a bolt means it is the force is acting at, or which the force acts to the centroid of the connection. Now this is not very dissimilar here. It is the same. Now we'll just see what really means. And then we have balanced welds, which is really a technique that we use to change the dimensions of the weld, which was to make it a direct kind of connection, direct force, by just doing some manipulations using some and force equations. So first of all, what we need to know here is the terminology. The size of the weld is essentially, as you can see, your weld is like it is something like a quadrant of a circle, and you can see that this width is called the size of the weld. This A is known as the size of the weld. And then if you just connect these, and this length is known as the effective throat. Okay, and the effective throat is basically it is a perpendicular line connecting these, which will be acting. This will be like at 45 degrees from here. And then length of the weld is the total length of the weld. Like for example, in this case we have LW1 on this area, and then we have LW2 and LW3. Now using all these we get something called the area of the weld. Okay, now area of the weld means it is not the cross-sectional area. It is not the cross-sectional area. It means the entire area which actually transfers the shear, and also something that you need to know is in welded connections the force is transferred through shear. Okay, so the total area that is available to transfer the loads through shear is called the area of the weld. So it is simply the effective throat. This is the effective throat times the length of the weld, the total length of the weld. This is what we called the area of the weld. So there are some limitations that has been given in the manual regarding the choice of A, because when we go into the design, we see we have two variables. One is the length of the weld, and then them and design for the other. Usually we fix the size of the weld as per these specifications, and then we design for the length. Moving ahead, the strength of weld is given by this equation, which is Rn is equal to Fnw times AWE. AWE is area of the weld, which we just discussed before, and then Fnw is calculated using this equation, which is Fnw is 0.6, Fexs. Fexs is the strength of the welding material, strength of the you call it filler metal, okay, or which is the type of the filler that we use to to do the welding process. And then this theta is the angle between and the orientation of the weld. Now in this case, for example, these two welds are parallel to the line of action of the force. So which means the theta value is 0 here. Okay. While in this case, it is perpendicular. This is like 90 degrees. This weld is oriented at 90 degrees to the line of action of the force. So in this case, the value of theta should be taken as 90. We'll see in the problem how it is implemented. Then something that we need to discuss is direct force. Okay, direct force is when the line of action of the force passes through the centroid of the weld. Okay, now you see that the centroid of this weld lies somewhere over here, and when the force acts exactly at this through this, it is called direct force. Even in this case, the difference between these two diagrams is that there is no weld on this side. We can design it that way also. Like if you don't want to apply weld here, you can simply use welding on just the opposite sides over here. You can do that. Now, we are clear about this. When the force applied to the weld passes through its centroid, it's called a direct force. And then we have the idea of balanced weld. Suppose we are talking about, in this case, if you might have noticed in the previous case, you see that both of them are plate. You know, when you apply a force on the plate, you assume that, I mean, it's a compression or a tension member. The force passes exactly through the centroid. That centroid lies over here, and the centroid, when you make the length of these two centroids, I mean, when you weld it such that these both lengths are the same, you're going to have centroid lie on this line. Suppose you're talking about something like an angle. Suppose you have connected an angle onto the yeah. So that is when the idea of balanced connection comes into picture. For example, you can take a look at this picture. You see that the centroid of an angle is never at the center because of the material on this side. The centroid has shifted slightly towards this side, this end. Suppose that you have made equal lengths of weld. Your centroid of the weld is going to be here, but the centroid of the line, I mean, centroid of the force and the centroid of the cross section is lying somewhere over here. So this really induces a moment here. Okay, this induces a moment. Now, to avoid the moment, what you do is you really decrease the length over here and you increase the length over here so that the centroid of the connection shifts towards the centroid of the cross section, making it direct. Okay, is balanced weld means you're really manipulating the length of the weld such that it passes through the line of action of the force, making it a direct force. For that, what we do is we use equilibrium. Okay, we take, for example, suppose you have a total force of T acting, tension acting over here. And this force is usually force. What does it? It is shared between these three forces. You have F1, you have F2, and F3. Now that gives you the first equation, summation of forces. Total tension equals F1 plus F2 plus F3, where F1, F2, F3 are the contribution from each lines of the weld.
Now, if you take a moment about F3, if you take moment about F3, you take moment about this F3, the left hand side you have moment acting because of the tension, which is Ty. You see that it's acting at a distance of Ty, so you have a moment here. And on the right hand side, you have F2, which is acting at what? Half length. F2 acts at half the length, means it's the leg size, one of the leg, while F1 acts at the whole length. So you have F1 times L plus F2 times L over 2, which is equated to Ty. You have two equations and you have two unknowns, and from that you really solve. You get, do this, you see that this length is known, but these are the two unknowns. We'll call it L1 and L2, or L3 and L1, whatever, and then we solve that, get the value of that is regarding balanced welds. Now, something also that we need to do, it is a check. Basically, it's a check. It's called check on the base metal. Okay. Now you are really check before, so that is like the strength of the weld should be less than two of these things. Base metal yielding, base metal rupture. Now you see that LW is the same. What changes is 0.6 Fy, and this is 0.75. There is a mistake here. This is supposed to be 0.75 times 0.6. Okay, I have forgotten to do this here. So it's easy to study because Fy is the yield strength. Now, if you want to get the shear strength, you have to just multiply it with 0.6. So this is the tensile strength, this is the shear strength. Now, when it comes to rupture, it is 0.6 times Fu, but you have to use, while in rupture, you have to use a factor of safety of 0.75. So that's what we use here. So now I think we are in a position to start design examples. You have any question here?
The explanation there was lagging of the, but I hope it will be clear with the examples.
The explanation is lagging with the screen.
I mean, also the voice was cutting.
Only the last minute, like 2 minutes. So,
Okay, I think my connection was out, so I will just explain again. No problem.
yeah, with examples it will be very clear.
Yeah. Okay. Fine. Just give me a moment. And now the voice is clear. Okay. So what I was saying was, while we're designing for the welds, we have to also make sure that the base material is strong enough to carry the loads. Like your weld strength of the weld should be less than two criteria. One is 0.6 Fy LWT, which is actually the base metal yielding, and you have something called 0.75 FU LNT. This is supposed to be 0.75 times 0.6 FU. I just missed, it's a typo, which is called the base metal rupture. Okay, so this is something that you need to check. Your base metal should not fail before your weld fails. So that means that's a big design problem, because you have designed a weld to be safe, but if your base metal fails, it is something that you have to be worried about, because you have made the connection right, but the connection did not fail, but the material failed. So you have to, in that case, if you're in an actual design position, you'll have to probably increase the thickness of the base metal, or you'll have to adjust some other parameters such that the base metal does not fail. So now we'll go into a couple problems where we'll design direct force in a weld subject to direct shear, and then you have a weld balanced weld problem, which will be pretty straightforward. So I hope the idea is clear. So I can just revise this if you want to. We have the key things that we need to know is that for a welded connection, these are the terms that you require. This is called the size of the weld. When you connect these and then you draw a 45-degree line, you get something to meet this point. You get something called the effective throat, which is the part of the cross section which is effective. I mean, which it is like a conservative. In fact, in real life, probably even a part of this might be active. I mean, might be active, but in design, you just make sure that your section does not fail. So you take something called the effective throat, and then the length of weld is the actual length on the periphery of the cross section of the material of the base metal where you really weld. So you have, in this case, you have WL, I mean length W1, length W2, and length W3. And when you add all of them, you get something called the length of the weld, and then the area of the weld is calculated using this equation, which is essentially effective throat TE times length of the weld. And then you have limitations for A. So as I told earlier, when we're designing, we end up with L and area of the weld. So you have to a length of the weld and area of the weld. So you have to fix one of them and design for the other. So usually we fix the A value and then find the length required. Okay. And then you have this equation. This is from the manual. Now you have something called the direct force. So the first problem will be on this particular type connection. And then you have something called the balanced weld. It is when we adjust the length of the weld so that the cross section, the centroid of the weld is located on the line of action of the force, or the centroid of the cross section, which makes it like a direct connection. So these are the equilibrium equations that we use to find the lengths, and these are the checks that we do. So now let's move into the problem. Okay. So the first question, you can take a good look at the picture. You see that you have two plates. Both plates are of the same thickness, but the width is different. Okay. And now the question says determine the size and length of the fillet weld. It is a type of weld, and for the course you're only using fillet weld. to transfer T ultimate, so you don't have to find the ultimate load. It's given to you for the lap joint shown. Use E70 electrode. This is the strength of the electrode which we require later on. And then A572 grade 50 steel, that is the material, that is this material. We require this for checking the base metal yielding and base metal rupture. And then using two types, two configuration of welds. The first configuration is using welds along it should be the opposite sides. What I mean is we're just using weld on these opposite sides. We don't use the weld here for the first example, and for the second example use welds on all three sides. Okay, and let's see how the inclusion of yes.
Yes, if the ultimate load is not giving, we calculate the capacity of the base metal, right?
Yeah. The second problem we'll see that you are given cross section and then you have been told to design the welded connection or the capacity of the member. So in that case, we'll have to do the old one. We have to check the yielding at gross section and rupture at the gross section. The net section. That's something that we'll see in the next question. In this case, I've just simplified this. You just have a TU given to you, and this is how it looks on this side. So in this problem, essentially what we're going to find is the length of these. Okay, and you might have figured it by now that in this case both the lengths are going to be the same, because the centroid, you need to keep the centroid here at the center of this material. So center of the cross section over here, center of this. This is something that you keep in mind. You just have to design one of the lengths that should be applied for both. And now we find the strength of the weld. The strength of the weld is found using this equation phi R and W, which we just discussed a few minutes back. So you have phi FNW AWE. Now FNW is something that we need to discuss. There's 0.6 FEXX, which is the strength of the weld, times 1 plus 0.5 sine raised to 1.5. Make sure it is sine to the power of 1.5 theta. Now FEXX is 70 KSI. So that is given in the question. It is E70. And suppose you're given E60, you'll have to use 60 KSI over here. So you might get E60, E70. I think for the term project it is E80. So in that case you'll have to take FEXX as 80 KSI. That's it. Okay. Now the unknown here is theta. Now from here it's easy. You'll understand the orientation of this weld is parallel to the line of action of the force. So theta is 0. So when you substitute all the values here, you get the value of also you need to find AWE. I did not mention that. You need to find which is equal to 2LW times TE, because this is how it is. You have two welds. I'm naming this as LW. Okay, so what is the total weld? The area of the weld of this one is what? LW, length of the weld, times the effective throat. Now you have two of them. So you have 2 LWTE, where TE is 0.707A and LW as it is. So when you substitute all of them into the equation, you have 0.75 times 0.6 FEXX, you substituted 70, 1 because theta is 0, and then the value of AWE as this one. So you end up, this is what I told earlier, after you substitute all the values, you boil, your phi R and W boils down to these two terms. So you have to fix one of them and design for the other. Okay, so in this case, or usually what we do is we fix the value of A because that's more reasonable, because A depends upon the minimum value and the maximum value of A depends upon the thickness of the base metal. Okay, the minimum value of uh, of of this is 1/4 of an inch. Now I need you all to go into manual where this has been discussed. So if you go into table J 2.4, which is on page 16.1, 16.1, page 111, you have the sizes of weld given. You see that we have used 5/8 of an inch, 5/8 inch. So for that particular thickness, the minimum size of the weld is 1/4 of an inch. This is available in the manual. Okay. And then the A maximum is again based on the discussion we just had a few minutes ago. We can just bring that up again so that we understand it better. You see how it is. A minimum is taken from the manual directly. This is really dependent upon this thickness. Okay. Now A max depends upon the thickness of the material. If the value of T is less than 1/4 of an inch, the maximum value of maximum value of A is T itself. Now, if the value of T is higher than 1/4 of an inch, quarter inch, the value of A max is T minus 1/16 of an inch. Okay. So in our case, the value is 5. The thickness of the value of T is 5/8. Okay, which is greater than 1/4 of an inch. So the A max value is 5/8 minus 1/16. So let's go back to the problem. So that's how we got this number. So now you can pick a value. In this case, I have taken 1/2 inch, it lies between this. So once we have fixed the value of A, you just are left with, when you substitute all these values, you put the value of A as 1/2 inch here, you get 22.27 LW. Okay. So this is the total strength of the weld. Now if you just take one of them for checking the base metal yielding and rupture, just take one of them. Okay, so in this case you know that both of them equal, so you can take phi R and W of the first one. You can take even the second one, it doesn't matter. You take the first one, which equals 11.13 LW. Okay, this is the strength of one of the weld among the two. So now you need to check the base metal yielding, base metal yielding, which is 1 times 0.6 Fy times length of the weld times thickness of the blade. So when you're doing the base metal yielding, you just have to consider any one of the weld which is in which is lying on this side or this side. You don't have to worry about weld over here because tension does not control. Okay, you're worried about the shear in this part. So 0.6 Fy, you substitute the length of the weld is Lw, thickness of the plate. You take the smallest thickness. In this case, we have the same thickness. Suppose you have two thicknesses, you take the smallest one, because it's clear, because the smaller thickness will have lower capacity. So you get 18.75. Substitute the values of Fy. In this case, we used Fy. For rupture, we use Fu. Substitute all of these, you get a value. Again, it's 18.25. I mean, it's 18.75 here and it's 18.25 here. Both are higher than the capacity of the weld. So which means it's safe. You can go ahead. Now, what we do is, after this check is done, it's easy. We're just equating phi R and W to the ultimate load. So which is 22.47 Lw equals 140. You get the value of Lw rounded to the nearest 1/16th of an inch. You get Lw. You have to remember, keep this in mind, that you had calculated Lw, which is only one of the length. So the total length is twice Lw. So you get the total length of the weld. I hope this is clear. You have a question? Anyone?
Clear.
Okay. Now this question is very similar to the first one, except that I have also included weld on this side. So which means that due to the contribution of this weld, the Lw that we get here will be less than the previous problem. That is something that we'll find out now. Now the capacity of the weld is same, but something that you need to keep in mind is that you have two values of this is FNW. I mean FNW. You have two values of FNW because you have two orientations of the welds. Like you have one weld which is lying like this, and the other weld parallel to the line of action of the force. So FNW 1, you get it as 0.6 times 60, and FNW 2 is 0.6 times 70, and this is 1.5 because we substituted the value of theta as 90. So you get, this becomes 1, so you get 1.5. That's how 1.5 came here. Area of the weld is length of the weld times effective throat. Now you see that you have to calculate two areas here. One is area of this one and area of this one. Area of this one is same as this one, so you have to calculate two of them. AWE1 is 2 Lw because we are considering this and this point times the effective throat. Now we have from the previous calculations, we plan to take A is equal to ½ inch. So when you substitute that, you get the area of weld on these opposite sides as this value 0.707 Lw. AWE2 is a constant because you know the length of the weld here, because the width of this plate has been given to you in the beginning. I think it's 7 inch. So you know the length of the weld here, and you know it is a constant value. Now you substitute all of them, all what you have calculated here, into this. Phi R and W is 0.75 times what? 0.6. You have 0.6 times 60. This is from here. FNW1 0.6 times 70 times area of the weld, which is LW 0.707, and then you have 0.6 times 70 times 1.5, which is FNW and AWE2. So you get a value of 22.27 LW plus 1.16, I mean 116.71 kips. This is in. Now you have to check the base metal shear yielding as well as rupture, which is similar to the previous one. I've just showed the steps so that you don't miss them out. It's the same. But in this case, what you need to remember is in phi, R, and W, you have two terms. Now, this term need not be considered because it is part of the weld. This part of the weld. Now, this part of the weld and this metal causes a tension here. It is not shear. Okay. And it is safe in tension because the TU which is given to you, it has already considered the yielding and rupture. So it is the safe value that is given to you. So you don't have to check for tension. You need to only consider the failure around the opposite welds. You do that, you see that the strength of the base metal from shear and yielding is greater than the strength of the weld. Now you are in a position to to easily substitute all of them to phi R N W equals T ultimate. Substitute all of the values, you solve it, you get the value of LW as 1/16th of an inch after you round it off, and you see that the total length of the weld is 9 and 1/8 of an inch. So this is an example in direct force. Now let's do. You have any question in this one? Anyone? Is it clear?
Clear, yes.
Okay. Now let's discuss about balanced welds. I've already given you a picture of what balanced welds are. You basically manipulate, you play with the lengths of the weld so that the centroid of the weld shifts to the cross section, shifts to the centroid of the cross section, making it essentially a direct member subjected to direct shear. So to a direct force because it involves both shear and tension. So it is a direct force. So you have F1. You can say this is F1 acting in this direction, and this is say F2 acting in this direction, and this is F3 acting in the opposite direction. So your F1 should be F1 is equal to phi 0.6 Fe times the effective throat, okay, times the area. So that should be less than the metal shear, which is yielding and rupture, and your F2 also should be less than the base metal capacity in shear, and F3 value is substituted directly. You don't have to check it against anything, and then you use the moment equation to get another set of equations. So you have two sets of equation. You have one set of equation from the force equilibrium and one set of equation from moment equilibrium, and then you solve for the two unknowns, which is L1 and L2. Now let's do a problem which involves balanced welds. Design the fillet weld to develop full strength of angle shown to minimize the effect of eccentricity, which means you have to, if you want to minimize the effect of eccentricity, it is a balanced weld. So this is another way of putting it. You have to use angle by 4/3 over 8, and the electrode type is E70. Grade of the steel is A570 to grade 50, and using LRF specs. L dash is 6 inch in the previous figure, and gusset plate does not control. So which means the L, which is, I mean, there are two legs. The leg which is on the gusset plate is the longer leg. So moving ahead, the step TU is not given to you, so you have to find TU. TU is not given. In fact, you are told to design for the capacity of the cross section. So to design for the capacity of the cross section, you have to design for the strength of the cross section. So this is the first thing that you studied in this course, which is yielding at cross section and rupture at net section. So here, this is pretty easy. You get the value due to yielding as 162, and the strength due to rupture as 158.39. Now this is something that, the thing that you need to note here is it is 0.75 FUAE, 0.75. You know that, you know FU. Now AE is U times AN. Okay. Now this is a welded connection, so your AN equal to AG, because you do not have any loss in cross section because of bolt holes. So your AN, the net area, equals the gross area, but you still have a problem with U because of this is called the shear lag factor, if you remember, because your cross section looks like this. You're putting welds here and here. You see that this leg is not connected, only this leg is connected. So you have a value of U which is less than 1. So you cannot start off with a value because you do not know the lengths of the weld. Because if you remember, U is 1 minus x bar over L. For a welded connection, it is just the length is, x bar is known because you have the cross section, but L is not known because L is something that you need to find by the end of the design. So what we do is we assume a value of U, a reasonable value of U, and after we design the values of L, we check it to make sure that it is safe. So we go ahead to calculate a few values. If we calculate the value of F1, F1 is 0.75 times 0.6 FEE, FEXX, which is the strength of the weld, times the area, which is effective throw times the length. If this is L1, this is L1, so you get 31.5 TEL1, and F2 is calculated similarly, except that the length is different, so it is L2, and the unknowns here are L1 and L2. Okay. Now you see the how A has been taken, because we essentially assume A and design for L. So A, this is from the manual. This is based on the thickness of the angle, because it has been mentioned in the question that the gusset plate does not control. So this A minimum is chosen based on the thickness of the angle. Okay, and your A maximum is checked, and you get value. You assume a value of A, and based on the value of A, you find the value of effective throat. You substitute all of them here to get F1 is equal to 6.93 L1, and F2 is 6.93 L2, and F3, again you substitute all of them. You know the length here. Length is not an unknown here. You know the length. So your F3 value is 62.37. Step, is to check the base metal shear yielding and base metal shear rupture. Consider one of them. It doesn't matter. Consider, because here I've checked it against L1 because it is essentially the same. Here it is just the difference is just it is 6.93 L1 and it is 6.93 L2. You may consider one of them, like for example the shorter one or the longer one. It doesn't matter because you don't know which is short and which is long. Though you can assume that your L1 is going to be long, but you're just checking it against the variables. So it doesn't matter whether you use L1 or L2. So your 0.6 Fy length of the weld times thickness of the plate, 0.6. Your this is L1 and the thickness of the plate is 3/8. Substitute all of them, you get 11.25. And the base metal yielding is calculated. When you substitute all of them, you get the value of 10.97. In both cases, your phi R and W, the force on one of the weld F1 is less than both of them. So which means the strength of the weld is smaller than the shear strength, shear capacity of the base metal. So which means it's okay. Now we use the equations of equilibrium. The first equation is the force equation, sigma Fx equal to 0. You have the three forces. This is F1, this is F2, and this is F3. Equate them. You have one equation. This is equation number 1. And now we use the moment equations. Okay, you take moment about F1. So when you take moment about F1, the F1 term disappears and L1 also disappears. So when you solve this, you get the value of L2. Now if you know the value of L2, you shoot it back into this equation to find the value of L1. And once you have found the value of L1, you can check it against, since you have found the value of L1 and L2, you can just check the value of U. You see that the value of U is 0.87, which is less than 0.9. Now why did I say it is okay? Something that we need to check. You see, if you go up where we assumed the value of where we assumed the value which controls, we had assumed the value of 0.9. Now the value that we got now is 0.87. So the capacity, when you calculate 0.75 times 65 times 0.87 times 3.61 is 142. When you put the value of U as 0.87, is 12 kips, but you had already designed it for 158, which means it is safe. So since it is okay, you can assume the value of L1. You can round it to the nearest 1/16 of an inch, and similarly find the value of L2, and that's the end of the design.